Assalamualaikum everyone. So today we are going to continue our lecture with lecture 3 with the title Silicon Processing. Now before we go further, let's see the history of the integrated circuit. So the integrated circuit started by 1947 when John Bardeen, William Shockley and also Walter Brattain demonstrate the flow of electricity through silicon, which can be selectively controlled. So then it goes to 1958 when Jack Kibley of Texas Instrument invented the integrated circuit on the germanium. Okay, so this invention then won the Nobel Prize in Physics in 2000 for the invention. Half a year after that, Robert Noyce, which is the co-founder of the Intel, improved the IC design using the silicon as the platform. Okay, so the IC global market is now around USD 1 trillion a year. So what is integrated circuit? So integrated circuit is a piece of specially prepared silicon, or in another word we call here is semiconductor, where there are complex electronic circuit and micro manufactured circuit that being printed on the circuit itself, okay, on the silicon material. So if we look into the picture that's shown here, so if we open up our computer or handphone, you will see something like this one, right? So if we open up the cover here, okay, so you will see this kind of chip. Okay, so if we enlarge the view of the chip, the integrated circuit here, inside here there are complicated circuit that have a lot of function inside here, like diode, it can be transistor, it can be capacitor, and there are a lot more being printed on that silicon chip. So the picture here showing the silicon that being printed with the integrated circuit. So it is very small actually. There are a lot of chip on this one plate. Okay, so it is going to be dies, and then this is the size of the final integrated circuit that will be covered in the packaging and then inserted into the computer or the electronic part. Okay, in a simple word, we can see that integrated circuit is nothing more than just an advanced electronic circuit. Okay, so this one it contains, as I mentioned previously, there are transistor, resistor, capacitor, diodes and many more. Okay, so the microprocessor found in computer and similar device are considered as integrated circuit. In one IC, they contains millions of microscopic electronic devices that I mentioned previously, like the diode, transistor, capacitor, and many more. Okay, so this all the devices here will be interconnected and built in layer. Okay, so we are going to look into this process later, one by one. Okay, so the IC usually will be around 5 to 25 mm size in square or rectangular. Okay, and the thickness will be around 0.5 mm thickness. Usually the integrated circuit that have been fabricated will have mirror surface finish, where none of the defect is allowable on this semiconductor wafer. Silicon is mostly used semiconductor material for the integrated circuit. So the reason is because of the material properties itself. We're going to look further later, and it is abundant, so it is easier to get, and then it also low in cost compared to the other materials. So germanium and gallium arsenide are less commonly used semiconductor material due to the availability and also the cost of the material itself. The basic integrated circuit manufacturing processes sequence is presented in this picture. So The first thing first is the pure silicon will be formed into the molten state, meaning it will be melted, and then it will be accumulated into ingot. This is the ingot. The first picture that here is the silicon ingot. We call it as ingot, and then this ingot will then slice into wafer like this one, and then the microfabrication of integrated circuit on the wafer surface will be performed, and then it is dies, and then wafer will be cut into chip and packaged into these things in order to protect it from any damage or any contamination. Now let us look into details on the material and also the process to get the silicon. The raw material for the silicon is sand, which is the silica, what we call as SiO2. Okay, so this material will be melted, and then it can become an metallurgical grade silicon, which is MGS. In order to produce the MGS, the highly purified quartz or silica will be heated with the wood and also charcoal in the arc electric furnace, where carbon electrode will be used. Okay, so this material will be what we call to will be heated more than 1090 degrees Celsius until you get the liquid MGS, which will be collected at the bottom of the furnace. Okay, so this is showing the chemical reaction between the material, and in the end silicon and also carbon dioxide will be produced. Okay, so here is the schematic diagram showing the melting process for the MGS. Okay, so this is, you will see the automatic vertical regulator, and then there will be what we call the input of the quartz and carbon into the furnace here, and then it will be heated. When everything is already melted, the silicon will be on the bottom here, and then it will go out through this outlet. Okay, so as I've mentioned previously, MGS is relatively cheap. This is due to the raw materials itself is silica or quartz. Okay, so which contain the sand and rock, so they are abundant. There are a lot of sand in this world. There are more than 26% of the crust of earth is silica. Okay, so meaning the sand. Okay, so in 2008 MGS is around $3 per kg only. $3.20 per kg. After we've got the MGS, it has to be processed into electronic grade silicon, which is EGS. So to obtain the EGS, the purity requirement will be more than 1 billion times. Okay, so this process is done in 3 steps. So the first step is MGS will be reacted with the anhydrous hydrochloric acid at 300 degrees Celsius to form trichlorosilane, so HSiCl3. Okay, so in order to get the next part of the material. Next, the trichlorosilane will be distilled to obtain the electronic grade silicon. The last step is the EGS is produced via the CVD process, or we call as Siemens process. In here, the HCl3 and also the hydrogens will be supplied to this chamber, the inlet, and then the silicon will be what we call it will be evaporated on to this bridge. Okay, and then the gas that will be created will be the HCl in form of gas, and then it will go through the outlet here. Okay, so because this is a poisonous gas, so it has to be collected in order to make sure that it will not be what we call harm the user, the worker. Okay, and then if the EGS need doping, then they will introduce doping gases, for example ASH3 or PH3 into the reactor. Okay, so that the silicon that being created will be having the doping effect on it. So compared to the MGS, EGS is very expensive. So this is due to the manufacturing process itself is very expensive and complicated. The next one is due to the chemistry is dangerous. As I mentioned, the gas form is toxic and corrosive. So PH3 and ASH3 are very poisonous gases. So if you search, you will see that PH3 will be has been used as a toxic killing agent in the World War II. Okay, so the next is because the process itself is very slow. So you can gather like 1 kg per hour. But the high price does not affect microelectronic industry. The added value in the manufacturing chip itself far exceed the price of the EGS. So the EGS that created is polycrystalline. Okay, what is polycrystalline? Uh, if you see into the microstructure, we'll see separated grain of the material. Okay, so this is the grain. So this part is not good to the silicon for the electronic. Okay, so why? Because there will be a interruption of the electric flow inside the chip due to this grain. Due to that, the EGS will be further processed to form the monocrystalline silicon. So this silicon, which is the crystal lattice of the entire solid, is continuous. It has unbroken or what we call the grain is boundary. There is no grain boundaries to the edges. Okay. So crystalline perfection allow for manufacturing of devices, for example, like the VLSI. Um, that contain billions of circuit on the single chip. So this is an example of the VLSI. Okay,